Alright everyone, so last video we talked about the factors that affect the resistance of a metal, and actually I do need to make a correction. It is true that when the temperature increases for a metal, the resistance increases, and the effect that temperature has on a material depends on what type of material it has, and especially if it's a semiconductor, the effect is actually the opposite from a conductor like a metal. Anyways, that aside, what I want, what I specifically want to mention is that the effects of length and the cross-sectional area that we mentioned, I mean that we talked about, these are actually the same for any object or material that you have. Okay, uh, s- and it's because like in when I talked about this proof with the resistors, and even in this logic, even though I mentioned electrons, okay, while talking about these effects, you could just say there are your general charge carriers. Okay, they could be any charge carriers that your material or object has. And so these properties aren't just these two effects, okay, like uh, resistance being directly proportional to length, okay, and it being inversely proportional to area. These aren't just limited to metals, okay. It applies to any material or object, all right. And so in this video what I want to do is take it a step further. So I discovered these two relationships. So um, what I have is the resistance being proportional to length and inversely proportional to area. Let's actually develop this a bit more. And what I mean by that is, so let's keep it here, right? So okay, so resistance is proportional to length, okay, and we know that the resistance is inversely proportional to the area, all right. So if I combine these, okay, if I combine these, I'll use a different color. Okay, I should be able to say that the resistance is proportional to the product of these, right? It's proportional to this, it's proportional to this whole thing, okay. So it should be proportional to the product of length and the reciprocal of area, right? So this should be proportional to their product. This should be proportional, resistance should be proportional to their product, okay. Or if I want to write it in a neater way, um, in a more concise way, I could just say it's proportional to length over area, right? Okay. So pretty neat. So we summarize this in a single relationship, you could say. So this right. So we know that since it's a direct proportion, it basically means that your resistance is going to be equal to some constant into your length divided by your area, right? Some constant that's going to be here, okay, into your length divided by area. That's we know that's basically how direct proportion works. And this constant of proportionality, okay, in this equation, uh, we denote it as rho, and we give a name for it, okay. We give a name for it. We actually call it resistivity, okay. We actually call it resistivity. Resistivity. Right. So you might say, okay, so what we gave it a symbol, okay, fancy Greek letter, and we gave it a name. But what's interesting about it? What's the point of it? Well, resistivity is actually really interesting, and let me explain why. So let me choose a different color. In this equation, see, resistance. Okay, so it's equals. It has some direct relationship. Okay, a direct proportional relationship with the resistivity rho. But the main thing you can see here is in this formula we have set aside the length and the area. In other words, we have set aside the dimensions of our object, right? The effect that the dimensions have, it's going to be described by this term, right? We have set it aside, right? We have set it aside uh, from whoops we have set it aside from the resistivity. Okay, uh, so we have set it aside from this. So this by itself, this is basically what dictates the what change. Okay, so wait, let me fix my speech. Okay, so um rewinding. Okay, so this expression right here, this factor right here is what tells you. Okay, so what does what effect do the dimensions of your object have? Okay, what effect do the dimensions of your object? Okay, so not like that. Suppose say if what effect do the length and the area? So your let me go up a bit. So your length and your area. Okay, so these are enough. This expression is enough to tell you what effect these two have, okay, on a resistance. And so this the whatever is left here, your resistivity, okay, this is it should make a bit more sense now. This is not affected by your dimensions. Okay, this is not affected by the dimensions of your object. Okay, or your resistor, conductor, whatever you want to call it. So it's not affected by those uh, and have I been saying metal all this time again? So, anyways, it's any sort of material. Anyways, so as I was saying, since you have set the dimensions aside in this formula, okay, and this is enough to tell you what effect the dimensions have on the resistance. Okay, the resistivity, this constant of proportionality, this doesn't depend on the dimensions anymore. Okay, so resistivity, it this is very key. Let me write that down. uh, Resistivity, or rho, it does not, okay, oops, let me fix that, does not depend on the dimensions. It does depend on the temperature, but I think it's still pretty interesting that it does not depend on the dimensions of the material. It's you could say that this is, and yeah, it is true. It is a property of the material itself. Okay, it's a property of the material itself, regardless of what shape it might have. Like even if you uh, take, you know as that figure I drew turns out to be really actually useful here. So suppose you have this neat rod with some length and some area, but if you have the same material, I'll use the same color. Okay, suppose say I made this rod of copper. Okay, suppose say I made this of copper. Okay, and I'm going to make something else of copper too. Okay, this uh this very irregular shape. Okay, very irregular nugget shape. It's quite it's a bit bigger too than this. Okay, so from all perspective, for all intents and purposes, this has very different dimensions and everything from this. Okay, uh however, okay, so I'm just I'll keep one thing the same. So I'm making this of copper too. Okay, and also assuming that's the same temperature. Anyways, I'll not be talking about the temperature all the time here. So I'm just going to assume that's taken care of, or that's the same if you're comparing two things. But anyways, so both of these are made of copper, very different dimensions. They would have different resistances. Okay, let me choose a different color. They would have they're likely to have very different resistances. So your resistance is different. Okay, so your resistance is different. Okay, of these two. However, However, your resistivity is actually the same because you're using the same material. As I said, uh, you know, your your resistivity, this this does not depend on these dimensions. Whether it looks like a nugget or it's a very tidy looking rod, or whether this is bigger, this is smaller. resistivity does not care about that. Okay, it only cares about what the material is. Since it's the same material, your resistivity is going to be the same. So your resistivity rho is the same. Actually, speaking about rho and everything, and yeah, we have resistance here. It's actually, we have a very similar analogy to this, which we probably, most of the viewers have already seen some, this. Do you remember mass and density? So, what did you have? So, suppose say I have a cube of ice, okay, a cube of ice, and you have your entire North Pole. Obviously, this isn't to scale, but see, so your cube of ice, uh, you know, you have your small cube of ice. So, and this is your whole North Pole. I'll just assume that it's entirely made of ice. So, and this is your whole, and this is your North Pole. Okay, this is your North Pole, and this is just your cube. They are very different masses, right? It doesn't even warrant a comparison, to be honest. So they are very different masses, but however, since they're both made of ice, they actually have the same density, right? Actually have the same density. So again, it's really the same thing. Your mass is different. Your mass is dependent on your dimensions. Okay, your dimensions, your shape, etc. So yeah, that's basically your dimension. So your mass is different. Okay, it depends on your dimensions. However, your density, which is a property of the material itself. Okay, your density is which is a property of the material itself. And actually, wouldn't I was going to write the symbol for density here, but it's actually rho also. It might serve as a good intuition or analogy, both are rho, but I don't want to create confusion here. Anyways, so your mass, which does depend on dimensions, would it's very different for these two. Okay, so they have different dimensions, but your density is the same. It's only a property of the material itself. It's only a property of the material itself. And actually, I'm a bit surprised of how far the accuracy of this analogy of resistance and mass is going. Like in a previous video, I did use I did relate these two a bit, just to describe the formula for resistance, and I also did say we shouldn't over rely on that. But I myself am surprised how far this is serving us. But anyways, I think you got the idea that resistivity is a characteristic of the material itself, doesn't depend on the dimensions. And see, okay, so yeah, we are mostly done discussing resistivity, and I just have a few more things. Wait, I'll pause for a bit. All right, I'm back. So, yeah, the only things that we are left to discuss is, well, actually, there are some interesting things. One is this formula, as you can see. Let me rewrite this. So you have your formula is, and let me choose a different color. So let me choose a different color. This is R equals rho L by A. Okay, L by A, and well, you can use a I think those are called mnemonics, right? So you can use a mnemonic for it, um, namely replay. Okay, so suppose say you think about replay. Okay, and I'll ignore the y. Okay, so it's like I'll how can I draw the y in faint? Okay, so let's see. Hmm. Anyways, I think I'm spending too much time on it than necessary. Anyway, so let's just ignore the y. Let's just ignore the y. Okay, a bit. So, what am I basically talking about? Okay, so if you think about replay, so r here. Okay, r r here. You can think about the equals as e. Okay, so equals e. Okay, you can kind of think about the row as being a p. Okay, so row kind of being p. Okay, you have your l. Okay, you have your l. You have your l here, and this is it is a division, but you need to remember this division sign. But you have your area a, and you have your a here. Okay, and just ignore the y. Okay, just ignore the y. So that does help to remember the formula. Okay, so that's one thing. uh, the next is what is the unit for resistance? What is the unit for resistance? And I'll rearrange this equation to find that. So um, rearranging this equation, what I get is rho equals, let's see, r multiplied by a divided by L, right? Rho equals RA by L. All right. So to find the unit, I just need to plug in the unit, the SI units of all of these. So resistance has a unit of ohm, right? So resistance has a unit of ohm. The area has a unit of meter square, and the length has a unit of meters. And so one of these cancel out, and so what we are left with is ohm meters. This is the SI unit of resistance, right? So that is done. We know the unit, we know the formula, okay. uh, and we have a convenient way to remember that. Let's do a problem just to make things clear to us once and for all. So let's look at a problem. Here we have a cylindrical we have a cylindrical rod of some pure metal, okay, some pure metal. This and well just some side information. Suppose, say, this is 20 degrees Celsius. We're working at 20 degrees Celsius. It's going to be the same all the time here. So we have our wait I should have used a different color. So we have our pure metal cylindrical rod, and uh, we sling a cell across it. Okay, sling some cell across it. All right, and these are ideal wires. So we have so this cell has provides a voltage or EMF. Well, we'll talk about that later. So it provides a voltage of 3 millivolts. Okay, and because of that, you get a current of 2 amps. Okay, of 2 amps here. Okay, through this rod of ours, and we are given some more information, okay, specifically about the dimensions of this rod. This has a length of, let's see, um, 2.10 meters, 2.10 meters, and a diameter, okay, a diameter of 5.47 millimeters. 5.47 millimeters. um, Wait, I'll write that here, millimeters. All right. So what you're asked to do is find the resistivity rho. Find the resistivity rho. Okay, rho, and identify this metal. Okay, identify this metal. All right. First thing we need to find rho, and well, we did rearrange that equation and found that rho is equal to RA by L. Okay, so we need to find each of, we need resistance, we need area, we need length. Alright, the length is pretty clear, there is nothing for us to do anymore, so we just need to plug that in. The resistance, we don't exactly have it, but we do have our the voltage across this rod, and we have, for that voltage, what is the current, right? So we know that resistance is equal to V by I. Okay, V by I, and this is going to be equal to, let's see, 3 millivolts is 3 times 10 to the minus 3. Okay, and we have 2 amps. Okay, 2 amps, and this is going to be equal to 1.5 times whoops let's see, times 10 to the power minus 3, let's see, ohms, right? So we can plug that in, and let's see, we don't have the area, we don't have the cross sectional area, but we can also find that, right? We have the diameter and we know this is a cylinder. Okay, so for a cylinder, our cross sectional area is our cross section is a circle. Okay, so our cross sectional area is going to be pi r squared. Okay, we don't have the radius also, but we have the diameter. Our radius is just going to be half of that, right? So if your diameter is 5.47 milliliters, sorry, not milliliters, millimeters, 5.47 times 10 to the, okay, this is getting bad. I'll move it here. So if our diameter is 5.4, this much, okay, so 5.47 10 to the power minus 3 millimeters, our 10 to the minus 3 meters actually, our radius is going to be half of that, and what we have is this squared. Okay, and this is going to give us let's see, actually it's going to be some value, I won't uh, bother putting that in for now. Let's actually just plug all of this into the calculator. Let's plug all of this into the calculator, so that should work. I'll just set up my calculator first. All right, so am I recording? Yeah. So let's plug all of this into the calculator. So we have a resistance. Oops, oops. Oh, let's see. I'll position that. We have so it's Ra by L, right? It's Ra by L. We have a resistance of, let's see, as we found it, it's 1.5 times 10 to the power minus 3. It's 1.5, 1.5, 10 to the power minus 3. Our area, we can just plug all of this in. So it's pi times 5.47 10 to the power minus 3, right? Minus 3. I'll put this aside here. So minus 3 divided by 2. Oops, not 3, 2. The whole thing squared. So that's my cross section area, and uh, my length. I need the length. That's just 2.10 meters. That's just 2.10 meters. 2.10 meters. 2.10. Okay, so this gives me 1.6. I'll round it to three significant figures. 1.68 times 10 to the power minus 8. 1.68 times 10 to the power minus 8 ohm meters. Okay, we worked in SI units all along, so this should be ohm meters. Okay, so we found our resistivity, and they also, we the question also included finding the metal itself, what metal this is. And if you're a professional working in this field, all you do is you take out your sheet of data, your database or something like that, and search which metal has the same resistivity. As I said, resistivity is a property of the material itself. Okay, so you just match which resistivity value is the same as this. And for your information, if you do that, you'll see that this resistivity is at 20 degrees Celsius. This is awfully close. This is really just it is the same as that of copper. Okay, it is the same as that of copper. So this, it's you can say it's most likely, or you can really be fairly certain that this metal is indeed copper. This rod is indeed made of copper. All right, so that is the end. And well, just one last note. You can see that the resistivity is really small, right? Really small, and that is to be expected. Copper is a really good conductor. Our wires are made of copper, so it has to be a really good conductor and have this low of a resistance, right? So yeah, that is the end of this video. I hope we have covered most of the things about resistivity. And yeah, I'll see you in the next one. Study smart.